Okay, welcome. We will get started here in just a second. So we're going to pick up with chapter 16, where we left off last time. Give everybody a second to get in. Okay, so we've been talking about KSP, and we started talking about solubility product, which is basically what KSP stands for. And KSP is an equilibrium expression, and is typically an equilibrium expression for things that are kind of insoluble. So sort of unique to KSP is sort of the way that the reactions or equations are always written, because they are pretty much things that are insoluble. When we do see the equation on the, let's see here, on the reactant side, we have our solids. And on our product side there, we have our aqueous ions. So just letting some people in here. Okay. So a unique sort of aspect of our KSP is when we do write our expressions, it is typically only our products that are there. And that is, again, because our reactants are solids and they're not usually included in the equilibrium expression. So the other thing that happens with our KSP is because of that, typically these KSP values are really small. So they're really small, and they're essentially going to be reactants at equilibrium, which means they're essentially going to be insoluble. But as we talked about last time, there is some degree of solubility with anything that we kind of deal with. So even though, again, technically based off of the solubility rules, the guy is supposed to be insoluble in a solid, even if it's a small amount, there's going to be some degree of it sort of dissolving, and it's still able to sort of set up this equilibrium. So as we saw with the numbers, I think the other day, they are pretty small ones. Sometimes it's like minus 18, minus 20, minus 30 something in terms of the KSP type values, which would imply that for the most part, it pretty much is reactants in our solids that are there. But again, a little bit of it will kind of come through. So when we do have these type of problems, usually we're looking for solubility. And that usually is one of two types of solubility: molar solubility, which is obviously our moles per liter, our grams per liters, and they're very common sort of solubility that you need to solve for. And we do ice tables, or can do ice tables like we've done before. And again, you have your solid guy here, you got your positive ion, your negative ion over here. And they do sort of work like our normal tables that we've done before. we typically would start with 0 on our product side. We're not going to be too concerned with our solid over here. But again, a different sort of letter, if you will, like we talked about last time, that's used in these sort of problems is a lot of times people will use S. And so instead of X, for example, we'll use S. And S really is this right here. S is the molar solubility or molarity. So that's something that's slightly different than a normalized table that we've done before. But the rest of it is the same. You know, at this point, we'd go into our KSP expression, obviously solve for S in this case. And S again would give us our molar solubility. So there's really kind of almost two sort of KSP type problems that we come across. One is you're given the solubility of the compound, and that again could be the molar solubility in moles per liter. It could be something like grams per liter or any other type of unit, if you will. But whatever unit you're given in terms of solubility, you do eventually want to get it into moles per liter or molarity. And then you could actually just go right into the KSP expression and basically calculate the KSP. The other type of problem is when you're given only the KSP sort of value and you're asked to find the solubility. And what that means is you definitely need to do a ICE table here and again solve for S and then calculate it that way. So we did one example I think we finished up with last time. So I think we're on this example here. So why don't you take a couple of minutes here or so and figure out what is the solubility of silver chloride in water. The KSP is 1.6 times 10 to the minus 10. And some numbers that you might need: silver from the periodic table, if you don't got one, 107.9 grams per mole, and chlorine is 3545 grams per mole. All right, so take a few minutes, see what you come up with. We'll compare, make sure everybody's on the same page. Okay, so let's take a look. So we're dealing with silver chloride. So again, our silver chloride here will break apart into silver ions and some chloride ions. And in this particular problem, we're just given the KSP, so you really should do an ice table here. So initially, again, solid on the left here, not going to worry about it. We got 0 and 0. Again, we're going to use that S instead of X, so plus S and plus S, which means at equilibrium, we have S and S. So very similar to a regular ice table, again, just using some different letters there. And just like normal, at this point, we're going to go into our KSP expression. And again, in this case, it's just going to be our products, as our reactant is a solid. That means essentially we have S squared equals 1.6 times 10 to the minus 10. We're going to take the square root of both sides. And if we do that, we end up with an S value of 0.0000126. And this would be the molar solubility of it. That's what the S stands for, right? So that is the molarity of it. And we're not interested in moles per liter, but we are interested in grams per liter. So in order to go from moles per liter to grams per liter, we need the molar mass. So that's why these numbers are here. So the molar mass for silver chloride would be 107.9 plus 3545. And that's going to give you 143.4, we'll call it, grams per mole. Again, comes from the periodic table where you would get that. So essentially what this number is here is moles per liter, right, of silver chloride. Again, multiplying by the molar mass of 143.4 grams per mole, because we're interested in the entire thing, the silver chloride. 143.4 gives us something like 0.0018 grams per liter in this case. And that would be the solubility of silver chloride in water. So what does that really mean? That means that you could take 0.0018 grams of solid silver chloride, and you could dissolve that much in 1,000 milliliters or 1 liter, which if you think about it is not that much really, right? And that's why when we think about something like silver chloride, that's why we typically think of it as being insoluble, because for the most part it is, but technically speaking, you could get about 0.002 grams to dissolve if you took about 1,000 milliliters of water to do so, which again, like I said, not an extremely a big amount of that. Any questions on that calculation? Okay, so I think I got one more here. So why don't you give that a go? What is the concentration of the aluminum ions in aluminum hydroxide? So take a couple of minutes here and do that. And by the way, just to touch on that last one we just did before, some of you might be asking, well, isn't S the silver ions concentration? And isn't S the chloride ions concentration at equilibrium? And it is, but when we look at the relationship, say, between the silver and the silver chloride, it's a 1-to-1 relationship, which means that basically is the same number for the silver chloride together. Same thing for the chloride ions, like a 1-to-1 relationship. And so when you actually do solve for S, in most cases, it actually is the molar solubility of the whole thing together, because remember as well, if you did have some coefficients, you would put the coefficients in here, and then it actually would work out the same way going backwards as well. So When we do solve for S, it typically is the molar solubility of the whole entire compound. All right, so take a few minutes and see what you come up with here. Okay, let's take a look and see how we're doing. So again, we're going to start with our aluminum hydroxide, which again is going to break apart into an aluminum ion plus 3 hydroxide ions in this case. Again, in this case, we're just given the KSP, which means we should do a nice table. So is going to be 0 and 0 to start with. Change is going to be plus S. And again, remember, just like a normalized table, we do need to take that coefficient into account. So that's going to be plus 3S at that point. That is going to get us S and 3S in that case. Any questions on the ice table? Now, our KSP expression would be the aluminum times the hydroxide. Also need to cube it because of that same 3 that is sitting there. That means when we do put our equilibrium in there, we will end up with S times 3S cubed equals our 2 times 10 to the minus 32, as that's what this equals. So we need to do some some cubing there, and something that people sometimes do mess up on is the part where you actually do need to cube the number. So that's going to give us 27s to the 4th times 2 times 10 to the minus 32. So very, very common. People will cube the S part, forget about the number. So again, 3 times 3 times 3 is 27. So we're going to take 2 to the minus 32, divide it by 27, and that will give us S to the 4th equals 7.41 times 10 to the minus 34. We want to take the 4th root of that. And if you do get a number of 5.2 times 10 to the minus 9. Again, this would be the concentration of aluminum. If you want to stick with probably the right sig fig, since this is only has 1, you would probably round that to aluminum is 5 times 10 to the minus 9 molar. As we can see, aluminum here equals S in that case. Any question on that? Now, we could also, if we wanted to, find out the hydroxide concentration. The hydroxide concentration would be 3 times S, which means you would take 3 times 5 times 10 to the minus 9, and that would get you 1.6 times 10 to the minus 8. Or again, if you were sort of rounding, probably to 2 times 10 to the minus 8 molar. Any questions on that calculation? So again, people oftentimes will sort of mess up on the, should I multiply it by 3? Should I also cube it? Should I do both or not? And very, very common people will mess up on cubing the S, for example, but forgetting all about the number and just leave it as 3. So that's a very common sort of mistake. Any questions on any of those calculations there? So this is just a table, not from your book, but you have something similar. I just sort of showed you the different combinations that occur depending on if it's sort of a 1-to-1 relationship, 1-to-2 relationship, and so forth, in terms of the mathematical relationship that you sort of get. So let's talk about actually using KSP values to help us decide, what substance would be more soluble, or maybe what substance would be least soluble. And there's really sort of 2 things that you could do with the KSP value. And there's really only one situation where you could actually directly use the KSP values to help you determine solubility. And it is for when you are comparing salts that basically break apart into the same number of ions. So what we mean by that is if we take these 3 guys here, that is silver iodide, which means when the silver iodide breaks apart, we get a silver ion and an iodide ion. And my math tells me that is 2 total ions that you get there. That is copper 1 iodide When it breaks apart, you're going to get a copper 1 ion and an iodide ion. That also is 2 total ions on the product side. And lastly, here are calcium sulfate. When it breaks apart, you get a calcium ion and a sulfate ion, which again is 2. So because all of these guys here basically break apart into the same number of ions, basically what that means is, mathematically speaking, you're going to have the same calculation, right? It's all related to the 2 ions that are present. So in that situation, if you have everybody that you're comparing produces the same number of ions, you can use the KSP values to determine which one you would expect to be more soluble and which one you would expect to be less soluble. And it really just comes back to our basic idea of what K is, right? If we have a small value, that means we mainly have reactants, which in the case of KSP means we would think it is more solid. And if we have a KSP that is a larger value, that means we should have more products, which means it's more aqueous in that case. So the larger the KSP value, the more products you would expect. And that means that if you have more products, you should have more ions, and the only way to get ions is for something to dissolve, basically, right? Which means that it is more soluble. So if we looked up the values for calcium sulfate, copper 1 iodine, and silver iodine, what we would see is the value for calcium sulfate would be the largest KSP value. And that means if we were comparing these 3 guys, we would expect the calcium sulfate to be the most soluble, which essentially would mean it would stay in solution probably the longest. And we expect the silver iodide to be the least soluble out of that group. And we expect it to probably precipitate out first. So sometimes this is really helpful if you have maybe a mixture of a couple of ions and you want to precipitate out one while maybe not precipitating out the other, or you could kind of predict which one you would expect to sort of precipitate out first by comparing the KSP values. So again, you can only do that if everybody you're comparing produces the same number of ions. Now, let's take a look at an example where it doesn't produce the same number of ions. So for example here, if we look at this guy, which is copper 2 sulfide, that is 2 total ions, a copper 2 ion and a sulfide ion. This is silver sulfide, which will break apart into 3 total ions, 2 silver ions and 1 sulfide ion. And then we have some bismuth sulfide, which will break apart into like 5 ions, 2 bismuths and 3 sulfide ions. So in this case, if we're going to compare all these guys and we want to compare the KSP values, we actually cannot use the KSP values to compare these guys because they break apart into different numbers of ions. If we ignored that and decided I am going to use my KSP value here to compare, what we would actually see is this guy on top has the largest KSP value, and this guy on the bottom has the smallest. Which means if you went strictly by KSP, you would expect this guy to be the most soluble and this guy to be the least soluble. And if you actually do calculate the solubility through like an ice table like we've been doing, what you actually see is actually the reverse. This guy up here is actually the least soluble, and this guy is the most soluble out of those 3. So when you have guys that make more than one, the same number of ions, you cannot just strictly go straight off of the KSP value to compare which one would be more soluble. You do have to do a calculation like you see in this table. But again, if in the previous slide, everybody you're comparing does break apart into the same number of ions, you can go by the KSP value. Any questions on that? All right. So then let's talk about an important effect, which is known as obviously the common ion effect. And if you remember, we saw the common ion effect when we talked about buffers. And the common ion pretty much is what we talked about. And what the name implies, you have an equilibrium that's set up. So in this case, we're going to be talking about the equilibrium for that salt. And what you're going to have is an ion that is in common with it. And basically the presence of that common ion, just like what we saw with buffers, the weak acid and weak base, it will suppress the dissociation of it, which basically means in this case, you just think about the equilibrium expression or reaction. They're all pretty much set up like this: solid on the left, aqueous on the right, which means in order to have a common ion, you would have to have somebody that's on the right-hand side here being there, present. And Le Chatelier's principle will tell us if we add somebody that's on the right, it will shift to the left. And when it shifts to the left, it's going to decrease the solubility than it would be in, say, pure water. So the presence of that common ion will have a similar effect as what we saw with buffers. And the presence of that common ion will actually keep the salt together. It won't allow it to dissolve as much as it normally would. So let's take a look at an example like we have here, silver bromide. And if we were to calculate the solubility of silver bromide in water, we would just do our normal sort of ice table. So that's going to give us our silver bromide plus our bromide. We'll do our 0 and 0. We'll do our plus S, equilibrium S and S. Going into our KSP expression, which is our products. And no reactants because it's solid, which means we get S squared equals 7.7 times 10 to the minus 13. We're going to square root both sides, and we will get a molar solubility for silver bromide there in water of looks like something like S is equal to, I didn't punch it in wrong, try it one more time just to make sure, 7.7 to the minus 13. 8.8 times 10 to the minus 7 molar for our silver bromide, which, you know, roughly is something like 0.00016 grams per liter, which again is not very much being dissolved if you convert that into grams per liter. Any question on that calculation? So that's just like what we did previous examples. So in part B, though, we're interested in what the solubility would be if we didn't put it in just water, but we also had in there some sodium bromide. So when we look at sodium bromide, obviously when it breaks apart, we get a sodium ion and a bromide ion. So we would set up our same equilibrium here, our silver bromide breaking apart into our silver and our Br minus. So we're going to do the same thing. So initially we have 0, this guy, but the difference is in this solution, we don't have 0 for the bromide to begin with because we have some sodium bromide, which is going to be a source of Br minus. And because that's going to be a source of Br minus, we need to figure out the concentration. So this whole thing is 0.001. It's a 1-to-1 relationship to the bromide, which means this guy would also be 0.001. So the importance here is kind of like when you do a table for a buffer, you got to actually have a number there. And in this case, we do have 0.001. Change is going to be the same, going to be plus S, which means at equilibrium, we're going to have S and 0.001 plus S in this case. So just like we did on the left there, we're going to go to our KSP, which will give us S times 0.001 plus S equals our KSP value, which is the same value, and that was 7.7 times 10 to the minus 13. So because KSP is super small, and we know that the change part here, represented by the S as well, is going to be really small, why not make an assumption like we've done before, and we're going to assume that S is equal to 0. Now, clearly it's going to be even smaller, this change, because we have the common ion. We expect it to push back the other way, and the change part is going to be even smaller. Just like before, you can't get rid of all the S's, so this would be just the S that you're going to add a number to. So that would be the 0.0010 plus S, we would just turn into 0.001. So that would then give us S times 0.001 equals 7.7 times 10 to the minus 13. So I ran out of the room there. So we're going to take 7.7 to the minus 13. And we're going to divide it by 0.001. And that will give us a solubility of 7.7 times 10 to the minus 10. And again, this would be molarity there. Any questions on that? And just for reference sake, at this point, the solubility decreases very, very much from the left-hand side to the right-hand side. So just sort of maybe practical numbers here. Just what was that number we had before? Over here on the left-hand side in water, you basically had a solubility of 1.6 times 10 to the minus 4 grams per liter, if you converted it. When we had the common ion there, you ended up with a solubility of 1.4 times 10 to the minus 7 on this side grams per liter if you converted it. So you can see very much so the solubility decreases a lot as you have that common ion there. It makes the salt basically stay together and not come apart. You should check your assumptions. So you would check it the exact same way as what we did before. So we would take our 7.7 to the minus 10, divide it by 0.001, times it by 100, and you're nowhere even near 1%. And to be truthfully honest with you, in these sort of KSP values, because they are typically in most cases so small, usually your assumption will be okay, but it never hurts to check it just to make sure, but it most likely will be okay. Other questions on that? So again, what we see here is the solubility goes down a lot, right? So on the left-hand side in water, we can at least get 0.0001 grams in there. When we add that common ion to dissolve in that same 1,000 milliliters, we could only get 0.000001. That's a lot of zeros to say. And obviously that's a lot smaller amount of that solid that will actually dissolve. Any questions on that? Okay, so I think you have an example. So why don't you give that one a go here. We want to know what is the solubility of silver chromate in a solution that contains potassium chromate. So see what you come up with. All right, so let's take a look at this one. So we got our silver chromate breaking apart, and obviously we have the KSP for that. So that is clearly the thing that's going to set up the equilibrium. So we will have our silver chromate that will break apart into a couple of silver ions, plus our chromate. Now we also have it not in water, but in a thing of potassium chromate, which looks something like this, which is a salt. So it will break apart into a couple of potassiums and one chromate when it breaks apart. The concentration of this guy is 0.1 molar, which means the concentration of the chromate over here would also be 0.1 molar, as it's a one-to-one relationship. By the way, if you wanted to know the concentration of potassium ions here, you would take 2 times the 0.1 and it would be 0.2 molar, but we're not really interested in that. So initially here, we got nothing going on here. But again, because this is a common ion, we want to make sure that we do put our correct number here, which in this case would be the 0.1 being supplied by the potassium chromate in this case. Change part going to be plus 2s. Again, we want to make sure that we do get the 2s there. This is going to be 0.1 plus s, and that means at equilibrium, 2s and 0.1 plus s. Any questions on that table there? So like normal that we've done a lot at this point, we do want to use our expression, which in this case would be the concentration of silver. We also do need to square it because of the 2 times the concentration of chromate. And again, that does equal the 9 times 10 to the minus 12. We're going to put our numbers in. So that will give us, we got there 2s, and we need to square it, times 0.1 plus s equals our KSP value of 9 times 10 to the minus 12. Again, pretty safe bet to assume s is equal to 0 here. Again, that's a very small value. So again, it's going to be this s here only. We still need to make sure we square everything going on over here. So that would give us 4s squared times 0.1 equals 9 times 10 to the minus 12. Obviously, when we take 4 times 0.1, gives us 0.4. And we would then want to take 9 to the minus 12 and divide it by 0.4. That's going to give us that s squared is equal to 2.25 times 10 to the minus 11. We want to square root it. And if we square root, it looks like we will end up with s is equal to 4.7 times 10 to the minus 6. Again, this would be the molar solubility in this particular case. I think I missed a number there. Let me just double check real quick. Did I miss it? Hang on one sec. 4 times 0.1 and 9 to the minus 12 divided by that. Like I missed a 0 somewhere. Let's see here. And we want to square root 4.7 to the minus 6, I think. So, any questions on that there? And obviously, like I said, that would be your molar solubility. Again, if you wanted grams per liter, you need the molar mass and so forth. Any questions on any of those steps? And again, if you check it, 4.7 times 10 to the minus 6 divided by 0.1 times it by 100, and you're like 0.004%. Like I said, it's a good practice to check. If you maybe don't check it on these guys, you probably in most cases will be okay. And again, I won't say 100% of the time, and that's why it's good to check. But most of the cases, you probably will be okay. Any questions on common ions? So what we're seeing here is the presence of a common ion will basically decrease the solubility of a salt, which means it will stay together, right? It'll become that solid or stay that solid. Less of it is able to dissolve when you have a common ion present. That's why a lot of things, and not 100% of the time, but a lot of things are more soluble in just water than anything else, because there's no common ions in water, right? You have no H plus or OH minus usually. When you do have something that does have OH and H plus, it does affect it, obviously, but in normal cases, you don't have those common ions floating around. Any questions on common ion and its effect on solubility? All right. So again, in this particular example, the common ion in this case was the chromate. And that's why the 0.1 came over here to the chromate part. And the silver, there was no common ion with the silver. So it's not like you had silver nitrate or anything in there. So the only thing that was sort of common ion in it was the chromate. And that's why we had an initial value of it as 0.1. And then obviously that's why it had the 0.1 plus S. And again, there was no source of silver ions to begin with, so that's why it was 0 to begin with. Other questions on that? Okay. So another sort of major sort of effect on, you know, the solubility of a substance is pH. And as we talked about, and as you sort of saw in sort of group 1, a lot of times we do play with the pH a lot, and it can help in solubility. Could also help in keeping things insoluble as well. So the pH plays a pretty good effect on solubility, especially when you're dealing with insoluble bases or acids, basically things that have H plus or OH minus sort of in them. So the pH of the solution will have a pretty good effect on whether or not the solubility will increase or decrease. So as we just saw, basically the common ion will decrease the solubility of a salt. And in terms of pH, an insoluble base will be very soluble in acidic solutions, while an insoluble acid will be very soluble in basic solutions. So just to sort of illustrate this point and what we're sort of talking about here, let's take a look at magnesium hydroxide. And we have the KSP for magnesium hydroxide. And as you probably could imagine, it's magnesium hydroxide. So if you had to take a pretty good guess, you would hopefully guess that this is like a base, right? With the name hydroxide in it. So let's take a look at this. And if we did our sort of ice table like we've been doing, so if we take our magnesium hydroxide, plus our 2 hydroxides over here, and we do our 0, our change, plus S plus 2S here again because of that. And at equilibrium, we have our S and our 2S. This obviously would go into our KSP expression here, right? So that would give us S times 2S squared equals 1.2 times 10 to the minus 11. Doing a little bit of fixing here, that's going to give us 4S cubed equals 1.2 times 10 to the minus 11. And if we take 1.2 to the minus 11, we divide it by 4. We then take the cubed root of it. Actually, put the numbers in there. We get an S value in this case of 1.4 times 10 to the minus 4. By the way, I kind of went over it a little quick there just to make sure, you know, if you need to do something like, say, the cube root of something, right, on your calculator. And again, if you have a button that lets you do that, like a button that looks like this, where you can actually type in whatever it is, you can do that. If you don't have that button, by the way, you can take 10 to the caret type button and do 1 divided by 3 would give you the cube root, basically, right? So you take your answer to the power of 1 divided by 3, and that would be the cube root. 1 divided by 2 would be the square root. 1 divided by 4 would be the fourth root. So again, if you don't have that button, on my calculator, the button's not really 10. It actually is, my button looks like X with like a little square on it. So if you do that and do it to, again, 1 divided by whatever you're trying to do, that would get you sort of your root for it, if you will. So for example, on this problem, after you divide the 1.2 times 10 to the minus 11, you would take it to parentheses 1 divided by 3, and that will get you your answer. Now, in this particular case, that is our S value. And if I wanted to know the hydroxide concentration, it is equal to 2 times S, which means 2 times 1.4 times 10 to the minus 4 would give me my hydroxide concentration, which is 2.9 to the minus 4. So why would that be important? If I know the hydroxide concentration and I take minus the log of it, that is going to give me the pOH of 3.54. And that would tell me that the pH of the solution would be 10.46. So this illustrates a couple of things for us. It illustrates, in this case, because we have hydroxide RH plus involved, you can actually figure out the pH of that solution. So this solution, technically sitting the way it is, if you made it or had it, technically should have a pH value of 10.46, which is obviously basic, like we would imagine it would be with a name like magnesium hydroxide. So why would knowing the pH be sort of important? It would be important because if we decided we want to play with the pH, the pH in this solution is pretty much at 10.46. So what would happen if I took the pH above 10.46? In order to take the pH above 10.46, pretty much two things are going to happen, right? The major thing that's going to happen is the concentration of OH minus will then have to go up. And if you remember, OH minus and H plus are tied to each other. So if the OH minus concentration went up, the H plus concentration went down. So when we raise the pH here, that would be just like adding more OH minus. And Le Chatelier's principle will tell us that once we add more OH minus by raising that pH, we would expect the shift in equilibrium to head to the left. And if it heads to the left, on the left-hand side, we see we have solid, which means this is going to decrease the solubility, right? Because we're essentially adding more OH minus, shifting the equilibrium to the left and causing more solid basically to be made. Any questions on that part of it? Now, if you do the opposite and decide, well, my pH to start with was like 10.46, what I'm going to do then is drop the pH, right? So I'm going to lower the pH below 10.46. Same thing's going to happen if I go below 10.46. What that means is the concentration of OH minus is going to decrease, but the concentration of H plus is going to increase. So adding H plus to this equilibrium is going to have an effect when I do that. So if I add H plus here, clearly when we look at the equilibrium, there is no H plus involved, but there is a thing that likes H plus there, and that would be our hydroxide. So when you drop that pH below 10.46, the H plus that you're adding to do that, and the hydroxide that is there on the right-hand side of the equation, these two guys will come together and make H2O. And what that effectively is doing is removing OH minus. So by lowering that pH, you're supplying a lot more H plus. The H plus and the OH minus will come together to make water and effectively remove hydroxide from that equilibrium. And since you are Le Chatelier's principal experts at this point, you know that that should cause the equilibrium to shift to the right. And when it causes it to shift to the right, that means we're going to increase the solubility. So this is what it means, what it says up there, that an insoluble base like magnesium hydroxide will dissolve in acidic solutions, which is the blue part we just did there. When you put it in acidic solutions, you increase the H plus. The H plus and the OH minus that are there will make water, which is a liquid. And effectively what you are doing is removing the OH minus from that equilibrium and causing it to shift to the right, which means more of the magnesium hydroxide will dissolve in that case. Same effect happens if you have an insoluble acid, if you would put it in basic solutions. So as you go through, say, those qualitative analysis experiments, this is partially some of the reasons why in certain parts you make the solution acidic, then in like 2 seconds later you make it basic, and you go back to acidic and so forth, and you play with the pH a lot, because in certain cases having the pH at a certain level will basically keep a lot of ions in solution but allow certain ions basically to precipitate out. So again, pH is a very big advantage in a lot of cases in being able to basically help with the solubility, or in some cases you may want it not to help with the solubility. So by playing with the pH, you can obviously affect that. Any questions on any of that there? Okay. So we've now seen two major sort of things that affect solubility. The first being the common ion, which will decrease the solubility. We also see that pH can play an important effect on whether or not you will see a solid form. And now really the third thing in terms of will a solid form that really comes into play is the molarity, really, the concentration, as to whether or not you will actually see a solid form, even if it's supposed to form because of solubility rules. And that's where we could use our Q and our KSP to compare whether or not we would predict, if we mix these two solutions, would we get a solid that would form. So let's take a look at one and kind of see how that goes. So let's say, for example, here that we take a solution, 2 milliliters of a 0.2 molar sodium hydroxide solution, and we're going to mix it to 1 liter of a 0.1 molar calcium chloride solution. Will a precipitate form? So the first thing you probably want to think about is sort of your solubility rules and the ions that are present. So obviously, sodium hydroxide is a source of sodium ions. It's also a source of hydroxide ions. And calcium chloride is a source of calcium ions and a source of chloride ions. So obviously sodium hydroxide is a solution, right? Calcium chloride is a solution. So really the only things that could happen is the sodium will end with the chloride, and the calcium, right, will end up with the hydroxide. So based on solubility rules, hopefully you know sodium is pretty much soluble with everything. And that means the sodium chloride is definitely not going to make a solid. So the only other option would be the calcium hydroxide to make the solid, which I don't want to ruin it for you, but here's a KSP down there just in case you weren't sure. And by the way, if you weren't sure, you could look at a KSP table and try to figure out, which one is on that table, which is probably a pretty good indication that is going to be a solid. So what we really want to figure out here is, will a solid form? And we want to use Q to do that. So we want to compare Q to the KSP and see whether or not we will get a solid form. So now that we've deduced that it is the calcium hydroxide that will set up that equilibrium and possibly precipitate out, we could write our calcium hydroxide equation here. And Q, remember, would be calculated the exact same way as you do KSP, which means it would be the calcium ion times the hydroxide ion. And again, we do need to square it because of that. So we actually do need the concentrations of the calcium ion and the hydroxide ion in the solution. So technically we're taking both, we're dumping it into a beaker. So that's like a dilution, right? Which means we do need to get, we could use M1V1 equals M2V2 and figure out our concentration of those ions in that solution. We'll start with the sodium hydroxide. The sodium hydroxide really is our only source of hydroxide. So if we do M1V1, we could do 2 milliliters times our 0.2 molar equals our M2. And what I'm going to do, just to kind of make the numbers easier, I'm going to convert this into milliliters so that, everybody's in the same units. You can convert the other one to liters if you want, but, you can't use milliliters and liters, obviously, so you have to convert it. So the total volume is 1,002 milliliters in this case, which means if I solve for M2, I would end up with 2 times 0.2 divided by 1,002 gives me something like 3.99 to the minus 4 molar. And again, that is our concentration of hydroxide in this case. We would do the same thing for calcium chloride. Calcium chloride is our source of calcium. And by the way, it's a 1-to-1 relationship between calcium chloride and calcium, just like it's a 1-to-1 relationship between sodium hydroxide and hydroxide. So doing the same thing, our V1, I guess, would be 1,000 milliliters. Our M1 would be 0.1. Our M2 we're solving for, and again, 1,002 milliliters when it's all together. That would give us our M2 for this guy, which would be 9.98 to the minus 2. And again, this would be our source of calcium ion in this particular case. Any questions on that so far? So now that we have both of these, we could go into our Q, and our Q would be equal to our calcium times our hydroxide, which was the 3.99 times 10 to the minus 4. We want to make sure that we also square it there, right, for the 2. And let's see here, 3.99 minus 4 squared times 9.98 to the minus 2. That gives us a Q value. We'll call it 1.6 times 10 to the minus 8. First off, any question on how to calculate the Q value there? So once we do have the Q, we want to take the Q and compare it to the KSP. And in this case, the KSP value, which if it was not given to you, you obviously would have to find on the table, is 10 to the minus 6. And the Q value is 10 to the minus 8. That means that Q is less than the KSP, which means, again, it actually goes opposite of where that's pointing, which means it's going to head towards the product side. And in this particular case, we would not expect a precipitate to form. So remember, it goes opposite of where the greater or equal to's goes. And in all these guys, solids on the left, aqueous on the right. So if it's heading towards the product side, that means we should have ions. And that means we would not get a precipitate to form in this particular case. So remember that really the only ions that could come together that has the ability to form a solid in this mixture of these two things. The sodium hydroxide is a source of sodium ions and hydroxide ions. The calcium chloride was a source of calcium ions and chloride ions. So your only two combinations that could occur when you dump all those guys into a beaker together is the sodium ions could come together with the chloride ions. And based on solubility rules, sodium is soluble in everything. So right off the bat, you wouldn't expect sodium to make any type of solid. And that's what we're looking for here at precipitate, right? Which is a solid. So you wouldn't expect it to form a solid. So that's why we could cross out the sodium and the chloride. The only possible combination of a solid would be when the calcium ion and the hydroxide ion came together. And again, even if you weren't sure about solubility rules, if you saw that on a table, that's a pretty good indication that that guy's probably insoluble, as we see here with our KSP value. Other questions on that? So this is sort of the third thing that can affect solubility. Again, as we talked about earlier, sometimes people, when they learn those solubility rules, they believe 100% of the time it's always going to happen. This little table here says it's insoluble, which means no matter what the situation is, if I toss these guys together, I should get a solid. And again, that's not always the case. And it's not really always the case. As you can see here, concentration is also very important. For example, if you get your solution too dilute, you may not actually see a solid form. And to tie this back to sort of qualitative analysis experiments, that's why there's several steps in like group 2, group 3, where you take your solution, you put it on the hot plate, and you reduce down the volume. And the idea behind that is as you add reagents all the way through your experiment, all you are doing really is constantly adding water, right? Because most reagents are aqueous, which means they're water-based, which means every time you add drops, you're diluting your solution. And because there's a lot of steps in some of those experiments, if you kind of keep doing it without sort of concentrating down your sample, by the time you get to the very end test, which is the most important test in all these qualitative analysis experiments, your solution may be too dilute for you to see the solid being formed if it's that type of test or something of that nature. So just because we see solubility rules to say, you know, whenever you throw these two things together, you're going to get a solid, it is not 100% correct in that sense, because there are other factors that obviously can affect solubility. And those are three main factors: concentration of your ions, the pH of the solution, and the presence or non-presence of common ions are three things that can really affect the solubility of a solution or a compound. Any questions on any of that there? Okay, so let's talk about this here. And this is very relatable to our qualitative analysis experiments. And if you remember, our qualitative analysis experiments are essentially the idea of what is sometimes referred to as selective precipitation. And when we talk about selective precipitation, the idea behind that is pretty much what we've talked about. We want to selectively precipitate out one ion from a solution. So this would be a case where you have all these ions floating around in a solution, but you want to kind of take just one ion out of the solution, but leave the other ions still floating around. And you could use KSP to help you do that, to sort of selectively precipitate out ions. And that's what we see in this problem. So in this problem, what we're looking at is we have a test tube. And in that test tube, for example, we have bromide ions floating around. We have chloride ions floating around. They both have a concentration of 0.02 molar. So we want to add silver to it, right? So we basically want to take some silver ions, like from silver nitrate or something like that, and add it into the solution. And when we do that, if you're familiar with solubility rules, you will know that silver bromide and silver chloride are technically insoluble based on solubility rules. And there's the two equations and the two KSPs that are associated with those two solids, the silver bromide and silver chloride. So if you wanted to precipitate out those guys and you decided, I'm just going to dump the silver ions in there, who cares? Right? Well, the problem with that is, as you can see in the picture, one of those test tubes is silver chloride, one is silver bromide, which from my perspective, and probably yours as well, they pretty much just look like a white solid, which means if you wanted to selectively take out, say, the bromide without the chloride coming out, you can't just dump in the silver ions and go, I think this little white crystal is the silver chloride. I think maybe this white crystal is the silver bromide. Not really sure on that one. You know, you're not going to be able to know for sure that what is coming out is actually what you think it is. So we can use the KSP expression and our equations here to help us sort of figure it out. So let's take a look at this problem. What we want to do is figure out how much silver we need to add to precipitate out only the silver bromide, which means we want this to come out as a solid, and we want to leave the chloride ions still floating around free in the solution. So the approach to this is fairly straightforward. We're going to take our KSP expression, and that's going to be the silver ion times the bromide ion, and that's going to equal 7.7 times 10 to the minus 13. Now we're interested in the silver concentration, which means my silver concentration would equal 7.7 times 10 to the minus 13 divided by my bromide concentration. I already know in this solution that my bromide concentration is 0.02, which means if I put that number in there, I get a concentration of silver we'll call it 3.9 times 10 to the minus 11. So the question is, what does that number represent? What that number represents is the minimum concentration of silver that is needed to start to see silver bromide come out as a solid. So you would need to add a minimum of 3.9 times 10 to the minus 11 molar silver ions to that solution. And if you do, you will start to see a precipitate. And that precipitate most likely will be silver bromide in that case. But how do we know it's not silver chloride? We could do the same calculation for silver chloride using our KSP expression. Again, solving for the silver ion, we take our KSP divided by our chloride concentration, which would be 1.6 times 10 to the minus 10 divided by 0.02. Again, they both have the same concentration, those ions. And if we do that, we end up with 8 times 10 to the minus 9. So what does this concentration represent? This concentration represents the minimum amount of silver you would have to add to that solution to start to see silver chloride come out. So that means that if you start adding your silver concentration to your solution that looks like a solution, no solid in there, ions floating around, bromide, chloride ions floating around, and you get your silver concentration up to 3.9 times 10 to the minus 11, you should start to see white solid come out. And you can feel very confident that your white solid that you are seeing coming out is the silver bromide. You can even continue to increase the concentration of that silver all the way up to less than 8 times 10 to the minus 9, and you will still see solid coming out. At some point, as long as you keep it under 8 times 10 to the minus 9, you'll see solid, you'll see solid. At some point, you'll stop seeing solid. And that's an important thing because at that point, you can know, all right, I don't see any solid coming out. I've increased my silver concentration almost to 8 times 10 to the minus 9, but not there yet. And I don't see any more solid come out. I can know that I should feel very confident that I got rid of all of the bromide ions as silver bromide. I then could, after I'm left with all those guys that came out, add silver in a concentration of 8 times 10 to the minus 9. At that point, I should again start to see a white solid form. And that white solid that's getting formed at that point, I could feel pretty safe knowing that it is silver chloride coming out. And obviously, you can increase the concentration of silver at that point until you stop seeing anything come out. And then you know you successfully precipitated out both ions separately. So if I take my concentration of silver at 3.9 times 10 to the minus 11 molar, and I make it a little bit greater than that, but I keep it less than 8.0 times 10 to the minus 9 molar, that will make sure that the only solid that comes out in this particular case would be the silver bromide. And like I said, at the point where you stop seeing solid come out, you then could go above that 8 times 10 to the minus 9, and you should see white solid again, which would be the silver chloride coming out. And we have now selectively precipitated out one ion at a time, and we could be very confident that what we took out at each of those steps was the ion that we were looking for. And again, you can use KSP to do that. First off, any questions about everything I just rambled on about there? So just one point here to finish up this little question. Could we have predicted which one would come out first based on the KSP values? And the answer is yes, you could have. Because when we compare something like silver bromide, it breaks apart into a silver ion and a bromide ion, which is 2 ions. When we compare something like silver chloride, it also breaks apart into a silver ion and a chloride ion, which is 2 ions, which means we can use the KSP values to directly compare the solubilities of these two. And when we do, we see that the silver bromide has the smaller KSP, which means between silver bromide and silver chloride, the silver bromide should be least soluble. And that's why this question asks what it did. It asks, how can you get rid of the bromide first? Because the solubility of silver bromide should be less than the solubility of silver chloride based on the KSP values, because They do break apart into the same number of ions, and we can use the KSP values to compare. Any questions on that? Okay, couple of things. We will stop here for lecture for now. I know we went a little bit over here. So for lab today, the joy is we're going to keep lecturing. Yeah, so we're going to, I think we're almost done with this chapter here. We're going to get a little bit into nuclear chemistry, and then at that point, we're going to call it a day and a weekend and all that good stuff. So what's on tap for lab is whatever we got left of this chapter, we're going to try to make a little dent into the next chapter, which is nuclear chemistry, and then I'll stop the torture at some point and we'll call it a day. Any questions on any of that? All right, so since we kind of ran a little late here, let's shoot at 3:15. I'll give everybody a chance to get up and stretch and all that, and we'll start lab about 3:15. Again, come through the lab one. Hopefully it's the right time this time. If not, use the link in the module section. That one is always right. I'm not quite sure why I got all messed up on the other side last time, but use the one in the module section for the lab. And again, we'll start at 3:15, give everybody a chance to get up and stretch, and make sure you hit here if you haven't done so already. I'll see everybody in about 15 minutes.